Okay, let's look at the slides on the right. So we have a response. That response is for the second order systems. Okay. Okay, that response can be, the output response of second order or higher order system can be one of the following depending on the damping ratio, right? We pronounce zeta of the systems. This response can be estimated based on the locations of the poles on the S-plane, right? So the first one is underdamped response. I think we've discussed in the class before. Underdamped response, critically damped response, and overdamped response. That response is basically determined by the positions of the roots of the denominator of the transfer functions on the S-plane, right? Okay, let me go through again. Okay, now whatever transfer function that we have, g of s, okay, that is our transfer function, right? Okay, based on the value k, fv, and m here, we could, make a system to be one of the response of the system to be one of the, one of them, which is, it could be underdamped response, it could be undamped, critical damped, and overdamped, right? So depending on the value of m, v, and k, right? So now we can understand the S-plane itself, right? So if this, we have from, from this transfer function we obtain the roots of the characteristic equations. If it is on the real, okay, we assume that the system is stable, it will be on the left hand plane, right? So the system can be of this type, which is critically damped system, critical damped, if we have two equal roots. But this one, if we have two different real roots, we have an overdamped systems, right? But in other case, maybe we have a complex roots, all right, complex roots, maybe a plus j, b, put it there. Then this system becomes underdamped, okay, and then it is possible for the transfer function to get to be in the undamped systems if the roots of the systems is on the imaginary axis, plus jc, maybe minus jc, something like that, right? So we have a complete combination. So whereby we know that for undamped system, right, undamped system, no damping, we would expect something like, continuous, right? Because when we provide some input, the system will, oscillate continuously. But for underdamped systems, when we provide some input, we expect some oscillations, and then it will settle down because there's some damping there, okay? And then these two, right, is overdamped systems, right? Okay, we have the response for critically damped and overdamped system is a bit is the same, except the parameter will be different. Okay, now okay, having this diagram, we need to derive how do we actually calculate the parameter, okay, as shown in the slide of the output response for second order system, right? So this one, we need to calculate this, okay? Okay, now let's understand the positions of the roots on the S-plane, right? Okay, let me draw. There is imaginary, there is no real. Okay. Let's choose one complex roots. Right. So let's say put it here. Say this is our this is our JB plus JB. This is our A. Okay, this one is A plus JB. That's the position, right? The same things we have here. This is minus A minus JB. Okay. Okay, for analysis purpose, we just consider one side, okay, because they are mirror. Okay. Okay, now we have a point, the roots here. We should draw a line there, right, a vector to that point. Okay, now you see that if these points move towards this side here, right, so we're going to have undamped systems, right? If this point is actually moving to the real axis, it becomes overdamped systems. Okay, so now we need to find to represent the system in terms of complex complex plane, right, on the complex planes. So right now we need to see that if we move this point to this, that become undamped systems. That means undamped systems, the undamped system has zero dampings. That means our damping here will be 0 at that point, right? And then the damping here is 1 at that point, okay? And then between this one, or on the complex plane, the damping is less than 1, greater than 0. So any point that you pick on the complex plane here, your damping must be 0 to 1. If it is on the imaginary axis, it is undamped, it is 0. Okay, now we can say something about this. If this vector moves to that, so that creates the angle. Okay, the angle there. So that's 90. So we can find the zeta equal to, that's a zeta equal to cos theta here, right? Cos theta, right? Cos theta. So if it is in this side is minus 90, cos theta is 0, and then here cos 0 or minus 180, it becomes 1, right? So let's say cos theta, something zeta, minus 90, it's 0, right? 0 or minus 180, it's become 1. So we know that cos theta here, whatever angle here, that represents the zeta. So that angle here is, this is zeta. cos zeta, right? Okay, makes sense. Now we need to find the representations of what is A here, what is B here, right? So we need to find what is B, what is A. Okay. All right. To find A here, right? To find A here, we can use the trigonometry, which is cos theta equals to, say, so this is our omega n, natural frequencies there. Okay. So equal to A over omega n. That is our natural frequencies, right? Because why this is omega n or natural frequency? Because when we move that to the imaginary axis, that vector become the frequency. All right, I'll discuss it after this. Okay, that's omega n. So that means A, this one is cos theta is zeta, and then this is zeta, right? Because cos theta is zeta, so we have, yeah. So A is here, maybe you can put minus there, right? So this A is minus zeta omega n. Okay, now we need to find B. What is B? The B is, we can use the theorem Pythagoras. Okay, we need to find B. We know that B, we can say B is a omega D because it's a damped frequencies here, right? Yeah, I put B first. So that means we have B squared equal to omega n squared plus zeta omega n squared. Right. So and omega n squared 1, because okay, because this is negative, right? Because this is negative, you can put negative zeta there. Negative there. So 1 minus zeta squared, right? Then should be this omega n 1 minus zeta squared. Okay, this is our B, alright? So this is our B. You see that? So now our B is omega n 1 minus zeta squared. Okay, now we can we complete the model for this point here, A plus J B, which represent A minus zeta omega n, and B is this one, right? So now we know that A and B, that means whatever roots that we obtain from the transfer function that we factor the our characteristic equation, we will get something like this, right? Whatever value here, 1, okay. We have S plus A plus JB, right? And then we have S plus A minus JB. Okay, now we need to work out this. So we have to solve this, then we will get the final one. If you solve this, you know, get this, so you will, let me put this one first. S plus zeta omega n, which is represent A, plus omega n, which is 1 minus zeta squared. Alright, the same things, you need to multiply with the same thing here, S plus zeta omega n minus, this is J, put it there, omega n, 1 minus zeta. You can try this, okay? So when we solve this, we get this S squared plus 2 zeta omega natural frequencies S plus omega n squared. Okay, this is our standard form of second order systems that we derive from here, right? So now whatever value of our transfer function, we don't have to, you know, go back to this complex plane and then derive every single thing and then come back to here. So we can actually use this to represent the systems, meaning that if we have 1 over S squared plus 3S plus 2, we know that that's 2 is actually our omega n squared. Okay, so we can find the frequency, natural frequency. This is omega n squared. This is our zeta omega n, right? 3. Okay, so we know that, right? So this is when we know this parameter, we can then calculate this the TR, TS, and so on. So we stop here and then we continue after this.